So today we're going to be talking about pressure sensors. It's my computer one. There we go. So I'm going to start by drawing three terrible pictures to talk very briefly about what the basic different types of pressure sensors there are. So the first one I'm going to talk about will be a differential pressure sensor. So that might be something like this, where this is essentially one wafer. It's etched to leave behind a thin, usually very thin membrane. And then we might have another part of a wafer up here like so. And so this is what we would call a differential pressure sensor. So we might have some high pressure up here, some low pressure down here, and that difference in pressure is going to cause that membrane to deflect, right? So in this case, with high pressure on top and low pressure on bottom, the membrane would tend to deflect down. Okay, pretty basic. All right. Then the next type of pressure sensor, I'll draw it over here to the right, going to be real similar. Um, so there's my wafer with my membrane and all of that kind of stuff. And then I might have another wafer with a chamber like so. And inside here would be some reference pressure. Okay. And then this would be some external pressure. And depending on if the external pressure is larger or smaller than the reference pressure, then that membrane will deflect. Okay. So this is what would be called a relative pressure sensor because the deflection is dependent on the relative difference between the external pressure and the constant pressure inside the cavity. And then the last type of pressure sensor is going to be the exact same picture, except that inside of that cavity, instead of it being some reference pressure, it will be a vacuum. And then here is our external pressure. And so this is what's called an absolute pressure sensor because it measures the pressure with respect to zero, essentially. So all of these three different types of pressure sensors basically work the exact same way, right? The difference in pressure causes the membrane to deflect, and the amount of deflection can in some way, shape, or form be related back to that difference in pressure that was applied. Okay. So the first thing that we're going to do is we're going to get an understanding of essentially the behavior of the membrane. Okay. So I want to start by talking about systems where we might have a circular membrane. So I'm gonna save myself the embarrassment here and use my computer to draw a big circle. So the radius of this circle we're going to call A. And generally speaking, moving out from here is going to be in the R direction. Okay. So if we're moving radially away from the center where we've moved some distance R, obviously we could adopt a cylindrical coordinate system or we could have some theta as well and all of that kind of stuff, but that's really not going to matter to us because this thing is perfectly symmetrical. So whatever deflection we are going to get is only going to matter on the distance away from that center point R. So we're not going to worry about an angle and all of that kind of jazz because it's just beating something to death that we don't need. Okay. So this is kind of like a top-down view. And then from a side view, we might have something akin to this, right? Where the distance from here to here is just the diameter of the circle or twice A. If we had so let's say that the pressure down here was higher, and I'm just going to call it P, pushing up on this membrane like so, then what we would observe, and sorry, this is getting kind of busy, is some deflection W as a function of R based on our position away from the center of our circular membrane. And for what it's worth, this distance right here is going to be the height or the thickness of the membrane. So this is our side view. And then I'm going to label P is the differential pressure. So we might just say that's the pressure at the bottom minus the pressure at the top surface acting on the membrane. Um, A is the, again, radius of the membrane. H is the thickness of the membrane. And W as a function of R is the membrane deflection at a distance R away from the center point. All right. So mathematically, our membrane deflection is given by the following relationship. W of R is going to be equal to pressure times our radius to the fourth power divided by 64D. I don't know why I didn't write it down on that front page. I can't remember exactly what D stands for off the top of my head. I could have sworn I had it written down here, but anyway. But it's a measure in some sense of the ductility or the stiffness of that membrane. And I'm going to give you guys an expression for it in a moment, and then we're just going to fold it into the equation anyway. So P a to the fourth over 64D times 1 minus R squared over A squared squared. Okay. If D is equal to Young's modulus times our height cubed over 12 times 1 minus Poisson's ratio squared, like so, then we can rewrite this expression as 3 times PA to the fourth power 1 minus nu squared all over 16 EH cubed times 1 minus R squared over A squared squared. So while we're at it, let's figure out where the maximum deflection is going to occur. Okay. Or not necessarily where the maximum deflection is going to occur. We're going to discuss that, but what the value of the maximum deflection would be for a given pressure. So any thoughts on where maximum deflection is going to occur? The center. Absolutely right. So that would be R equals to 0. Okay. So our maximum is just W evaluated at 0. And so quite obviously then that whole 1 minus R squared over A squared bit is just going to go away. That's just going to look like 1. And so we're going to have 3PA to the fourth power times 1 minus Poisson's ratio squared over 16 EH cubed. And just to make sure everybody can remember this, I'm just going to put a note here that this is Poisson's ratio, which helps to relate stress and strain in a system. So as this membrane deflects, it's going to experience a longitudinal stresses, which will be in radial directions out, and then transverse stresses, which will be orthogonal to the radial directions out. Right? Um, the stress is experienced on the surface of the membrane. So let's look back up here, right? So as this membrane deflects upwards, what we're going to see is that in the region closest to the anchor point, this guy is going to stretch, right? So that's going to be in tensile, and this guy is going to be in compressive, but they're going to be equal and opposite. As we get to the center, the top surface is actually going to be under compressive stress now, and the bottom surface is going to be under tensile stress as it's getting stretched out. Okay. So there's going to be lots of plus and minuses in the stuff that I'm about to give you. And it's just because one surface is going to be positive and the other surface is going to be negative because one's in tensile and one's in compressive stress. So our radial stress, TR, as a function of R, is going to be given as plus or minus 3/8 times PA to the fourth power over H squared. I'm going to open this bracket. Then I'm going to have 3 plus Poisson's ratio times R squared over A squared minus 1 plus Poisson's ratio. Like so. And our transverse stress is pretty much going to be the exact same thing, except that we are going to have a little bit different inside that square bracket. So it's going to look like plus or minus 3/8 PA over 4, or excuse me, PA to the fourth power over H squared. And then here I'm going to have 3 nu plus 1 times R squared over A squared minus that same 1 plus nu. So where do we expect maximum stress to occur in this system? So when we had a cantilever beam, where did maximum stress occur? At the anchor. So this is, we could think of it as we wanted to like break it down into little parts. It's a whole bunch of essentially guided beam things where the region around the perimeter is the anchor of these individual beam parts as they're deflecting. So we should expect to see maximum stress at location A anywhere around, excuse me, our circular membrane. So I'm going to come in here and I'm going to say that the maximum radial stress, Tmax sub R, is just TR at A. And that's going to come out to be plus or minus 3/4 times PA. Actually, hold on. I'm sorry. I have a mistake here. These to the fourth power should be squared. My apologies. PA squared over H squared. And then the maximum transverse will just be TT evaluated at A. And that's going to be plus or minus 3/4 PA squared over H squared times Poisson's ratio. Okay. Yes.
So this man is basically like a trampoline.
Yeah. That's pretty much exactly it. Yeah. So you've got a structure around the outside edge supporting the membrane, and then the difference in pressure is going to cause the membrane, the surface of the trampoline, to deflect. Yeah. So trampoline is a perfectly acceptable analogy, except that The membrane isn't a mesh that air can easily pass through. Yeah. Yeah, that's exactly right. Okay. One last thing that might be useful is at the very center of the diaphragm. So at the center of the diaphragm, we're going to have TR at 0 will be equal to TT at 0, and that'll be minus plus 3/8 PA squared over H squared times 1 plus nu. There we go. So we've discussed deflection as a function of radial distance away from the center point, um, as well as maximum deflection. Stresses as we move away from the center point, and as well as exactly at the center point, and then maximum values for the transverse and radial stresses as well. Okay. So as far as a circular membrane, we know what we need to know. So now we're going to move on to a square membrane. Okay. And this is going to be a little bit grosser mathematically, but nothing too horrifying. So for a square membrane, get this guy out and just draw kind of a square here. I'm gonna put some dashed lines through this guy so we can develop a bit of a coordinate system. And I'm just going to use a Cartesian coordinate system. So this center point right here would be located at 0, 0. And we're going to say that this is our positive x direction, and this is our positive y direction, right? And the distance from the center point to the boundary, so this distance here, we're also going to call A. Okay. So the total length of this guy is 2A in both directions. Okay. So here's our top view. And then our side view picture is going to be pretty much exactly the same thing. So now with some differential pressure acting on the membrane, like so, what we'll see is some displacement, but now this displacement is going to be a function of both x and y. And then once again, this is our height. So side view. All right, so our membrane deflection, W as a function of x and y, is going to be approximately equal to, so not exactly equal to like we had in the case of a circular membrane, 12 PA to the fourth power times 1 minus Poisson's ratio squared. Actually, sorry, getting ahead of myself. PA to the fourth power over 47D times 1 minus x squared over a squared squared 1 minus y squared over a squared squared. And then substituting in for d, which is the same thing because it's based on the material, this is going to look like 12 pa to the fourth times 1 minus nu squared over 47 cubed times 1 minus x squared over a squared squared, 1 minus y squared over a squared squared. Um, Maximum deflection is still going to occur at the center point. So we could say that W max is just going to be W at 0, 0. And that'll come out to be 12 PA to the fourth power times 1 minus nu squared over 47 EH cubed. In this case, we're going to have normal stresses in both the X and Y directions. And so let's say that we would have Txx as a function of X and Y. And this will look like plus or minus 24 over 47 PA squared over H squared. And then this thing's going to get kind of large. 1 minus y squared over a squared squared times 1 minus 3x squared over a squared squared plus nu times 1 minus x squared over a squared squared times 1 minus 3y squared over a squared squared. Close this off. So this is our normal stress in the x direction. Our normal stress in the y direction is going to be essentially the exact same thing, but I'm going to write it out, except we're just going to swap x and y. So plus minus 24 over 47 PA squared over H squared 1 minus x squared over a squared. Goodness gracious, that doesn't look like a 2. Squared 1 minus 3y squared over a squared squared plus nu 1 minus y squared over a squared squared 1 minus 3y squared over a squared squared.
Is that 3y squared be 3x squared? Or then both?
Oh, no, this one is supposed to be x. Thank you for that, Hannah. Thank you. So for this configuration, maximum stress is going to occur essentially at the center point of each of the edges. So 0 plus or minus a comma 0 type things, right? So the 4 points that I've indicated in red. So our normal stress is going to look like plus or minus 48 over 47 times PA squared over H squared. And our transverse is just going to be nu times Tn max. So plus or minus 48 over 47 PA squared over H squared times nu. At the center of the diaphragm, we're going to see that our normal stress in the x direction and our normal stress in the y direction are equal to each other. And that's going to look like minus plus 24 over 47, 1 plus nu times PA squared over H squared. So these are all the relationships that govern the stresses that can be observed at various locations along the surfaces of the membrane, both in a circular membrane and in a rectangular membrane. So for the most part, just plug and chug related stuff, okay? So now let's talk a little bit about how we might extract an electrical signal out of one of these guys, okay? So probably the most obvious way to do this, one of the reasons why I've made it a point to indicate where maximum stress occurs and stuff like that, would be using piezo resistors, right? So we could integrate piezo resistors onto the surface of the membrane at the location of maximum stress, and that change in resistance can generate an electrical signal, right? So if we apply some bias voltage across our piezo resistors, as that resistance changes, the voltage is going to change across the resistors, and we can relate that to the differential pressure. Another way that we could do it could be to use capacitance. So if we scroll back up here to the very top and we look at either this relative pressure sensor or this absolute pressure sensor, if the membrane is one electrode and this bottom plate is right here is another electrode, then we have essentially a parallel plate capacitor. And as this membrane deflects, that capacitance is going to change. However, the deflection of this membrane means that that distance isn't going to be uniform, right? So that's going to make math all kinds of fun. Okay, so we're going to wind up using the Taylor series expansion and all that kind of stuff to sort out how that's going to work. But if these two pressures are equal, it's a parallel plate capacitor. If they're not equal, this membrane deflects. And so we see that, you know, D over here near the anchor point is going to be much greater than D at the point of maximum deflection. All right, so let's talk about piezo-resistive pressure sensors first. So essentially, I'm going to do this with a square diaphragm here really quickly. We might have a situation like, oops, that's not what I wanted. This, where let me define my coordinate system and all of that kind of good stuff again. So this is the y direction. This is the x direction. And we might choose to put some piezo-resistive sensor, let's say here and here, right? So these are locations of maximum stress on this square membrane. Okay? And for our measurement circuitry, we might choose to do something like this. So here's our DC bias voltage. Um, so simple Wheatstone bridge configuration, where let's say that this is going to be some R naught plus delta R. This will be a reference resistance R naught, so we might put it over here, away, like onto the bulk, so that it's not going to experience any kind of actual change as the membrane deflects. We might put another one over here, serving as a second reference resistor, and we configure it in this Wheatstone bridge configuration. We're going to work an example problem here in a moment to show that we can get an electrical signal out of this thing if our electrical signal is just measured across those 2 points. So let's say that as an example, we have a square diaphragm with an edge length. So 2A in this case is going to be 1 millimeter. Another way to think about this is A is half a millimeter or 500 microns. Okay. Our diaphragm has a thickness H of 10 microns. If our diaphragm is made of 110 single crystalline silicon, then, sorry, I didn't mean to scroll that far. So I'm just going to put 110 single crystalline silicon, which has the following properties. So Young's modulus is 170 gigapascals, Poisson's ratio 0.06. Longitudinal piezoresistive coefficient is going to be 71.8 times 10 to the minus 11 per Pascal. Transverse piezoresistive coefficient is negative 66.3 times 10 to the minus 11 Pascal. And we've got these two longitudinal piezoresistors. Having a nominal resistance. So let's just write this as R naught of 10 kiloohms. And what we want to find is the output voltage that's generated for a differential pressure of P is equal to 50 kilopascals. It should be capital. Sorry, my wife just texted me a picture of something. Let me see what the hell that is. Oh. Speaking of deflating people's tires earlier, my wife found a concrete nail in one of her tires, so she had to go get it fixed. She works in finance at a manufacturing company that is effectively just a large construction site, so it happens all the damn time.
And
So,
he's totally one person's parking spot, obviously.
all right. So just to revisit some things here. Hopefully we can recall that the relative change in resistance for a piezo resistor is going to be the longitudinal piezo-resistive coefficient times the longitudinal stress plus the transverse piezo-resistive coefficient times the transverse stress. We all relatively okay with that. We talked about it at length, okay? So, in this case, we could say that our delta R, so not our relative change, but just the actual change, and I'm going to put sub X here, because these resistors are aligned along the X direction, is just going to be pi L TL plus pi T T T times our nominal resistance. Well, what do you guys think TL and TT are going to be here? So where did we put our piezo resistors?
On the maximum.
At the maximum strain point. So I think we can say pretty emphatically that we scroll up here. This is our maximum longitudinal, and this is our maximum transverse, right? So 48 over 47 PA squared over H squared, and then just multiply that by nu to get our transverse, right? So I'm just going to make a note over here. TL is going to be 48 over 47 PA squared over H squared. TT is just TL times nu. So putting numbers into this expression, we would wind up getting the change in resistance for these horizontally aligned guys are going to be 71.8 times 10 to the minus 11 per Pascal. So that's just pi L times our longitudinal strain. So 48 over 47. Our pressure is 50 kilopascals. A was 500 microns. And H was 10 micron. So that's the longitudinal change in resistance. For transverse, I'm going to put minus here because this coefficient is negative. So 66.3 times 10 to the minus 11 pascals. That same 48 over 47, 50 kilopascal, 500 micron cubed, excuse me, squared. Ten micron squared. And then this guy is going to get multiplied by a factor of 0.06 because that's what the Poisson's ratio is given to us as. And when I threw this into MathCAD, I got a change in resistance of 865.813 ohms. So looking at the electrical side of things now, using that circuit that I showed you a moment ago, where this is R naught and this is R naught plus delta Rx. I'm going to call this voltage over here, excuse me, V2. This voltage over here, V1. Our output voltage is just going to be V2 minus V1. So V2 using voltage division is going to be whatever our DC voltage is which I don't think I said, but I usually just use 5 volts for this, times R naught over twice R naught plus delta R. Actually, yeah, that'll matter. V1 would come out to be VDC times R naught plus delta R over twice R naught plus delta R. And from this, our output voltage is just the difference of these guys. So I'd have R naught minus R naught minus delta R. So that's just going to look like, let's see, VDC minus delta R over twice R naught plus delta R. And I believe we can approximate that as that. So again, I'm sorry I don't literally have this written down anywhere, but I believe using 5 volts for VDC. So I'm just going to make a note here. I guess I could actually, we have everything. I can just double check it. So 5/2 times negative 865.813 divided by 20 kiloohms. I got negative 108.227 volts. I'm just going to see how different it is if I don't put the approximation there.
Did you think about 2010? You gave us 10.
Right. Oh, so that's the issue. Yeah, no, you're 100% right. So I put in 20, but I forgot that I already had that factor of 2 in there. So let me fix that. Thank you for that. You're 100% right. So that should be uh, good Lord. That's the thing that I want. Just change that to 1. 216.453. Thank you for that catch. Um, just for the hell of it, I am going to figure out. So not doing the approximation, I got negative 207 millivolts. So we're only off by 8 or 9 millivolts by making that approximation. So not really that big of a deal. Okay, what time is it? This class ends at 12:15, right? So one thing that we could do, if we were so inclined, is instead of using these reference resistors, we could put in transverse piezo resistors up here. Okay. So if we did something like that, we're now going to have what is essentially a delta R sub Y. Okay. So how do you think the equation that we got for delta R sub X is going to change to give us delta R sub Y? Based on the position of those piezo resistors and how they're oriented. So I would argue that instead of being in a in a longitudinal configuration, they're in a transverse configuration. So really the only thing that's going to change is that this 0.06 factor would get tacked onto the end of that term. And it wouldn't be on the end of the rightmost term because it's the long direction. Essentially, we're swapping which one is transverse and which one is longitudinal, okay? And so what we'd wind up getting in that particular case is a change of negative 791.387 ohms. And if we had a new configuration, I'm just going to zip through this really quickly. So VDC, so all of our R naughts plus delta RXs are going to stay the same. But those other resistors are now going to look like R naught plus delta RYs. So before I give you the result of the output voltage here, because I don't know that we have time to literally go through all of this stuff, I want us to think about something really quickly here. Okay? So why might we want to do this? So if we look up here, back in our problem statement, the transverse piezoresistive coefficient, transverse piezoresistive coefficient, the longitudinal piezoresistive coefficient, they're very close to each other in numbers, but they're of opposite signs, right? So essentially what we're seeing is that one of these resistors is going to get larger, while the other one's going to get smaller by roughly the same amount. So what do we think is going to happen to the output signal because of this?
It doesn't mean much.
It's going to double.
Oh, but they're equal.
But look at the configuration here, right? So let's frame this in another way, right? Let's say that this is just plus delta R, and this guy is minus delta R because the values of those resistances are so close to each other, but they're of opposite signs. So in this case, V2, which is this voltage here. Sorry, this is getting so busy. So that's going to be VDC. The one on top is going to be R naught plus, excuse me, R naught minus delta R. And then on bottom, we're going to have R naught plus delta R plus R naught minus delta R. So that's just going to be twice R naught. V1 BDC. Now we're going to have R naught plus delta R on top. And then twice R naught on bottom. And we take the difference of those guys. So we're going to have R naught minus delta R minus R naught minus another delta R. So these guys are going to cancel. That's going to get twice as large. The denominator is just going to be BDC over 2. Essentially, that term's just getting twice as large by doing this. So if we have a material like zinc crystalline silicon where our longitudinal and transverse coefficients are so close to each other, we can exploit that in order to boost our signal while changing no aspect of the power consumed by our system. All right, so let's talk about capacitive pressure sensors relatively quickly. I'm not going to bore you guys with a shit ton of math here, even though I took the time to do fun integrals. So capacitive pressure sensor, as I said earlier, going to be something kind of akin to this. Here I've got my membrane. I'm going to have some amount of insulation between the two wafers, and then I'm going to have another wafer down here where this guy right here is going to be either some reference pressure or vacuum. I think I might be putting too many C's in vacuum, but that's fine. Here's our membrane. And like I said, this is an insulator. Okay. So since the diaphragm displacement is going to be non-uniform across the surface, our capacitance isn't going to be as straightforward. So I can't say that C is just going to be epsilon naught A over D. It won't be that. Instead, it'll be some double integral where this integration occurs over the surface. And I'm just going to leave that as unbounded integrals for right now. E naught D I'm just going to say ds for surface over d naught minus w, where that w varies as dependent on position, right? Depending on whether or not we have a square diaphragm or a circular diaphragm, okay? So for a square diaphragm, what we'd find is that our capacitance will be equal to the integral from negative A to A, integral from negative A to A. So one of these is integrating in the X direction, the other one is integrating in the Y direction of epsilon naught dx dy over d naught, our nominal displacement, minus w as a function of x and y. Okay. This integral has no closed form solution. However, if wxy is much smaller than d naught, we can do a Taylor series expansion. So we could say that that term 1 over d naught minus w as a function of, goodness gracious, I keep screwing up that comma. X and Y will be approximately equal to 1 over D naught times 1 plus position over D naught. So if we substitute this expression into our capacitance equation, what we'll find is that our capacitance will be approximately equal to the double integral of epsilon naught over D naught times 1 plus position over D naught dx dy. Okay. And so I'm integrating from negative a to a in the x direction, and I'm integrating from negative a to a in the y direction. So that's essentially just the area of my plate, right? So I'll have epsilon naught a over d naught, which is just our nominal capacitance, c naught times 1 plus what I'm going to call w sub a over d naught, where w sub a is the average membrane deflection. Well, mathematically, we can calculate W sub A as 1 over 2A squared. So this is essentially just the area of the plate. Integral from negative A to A, again from negative A to A, of our position. Skipping through a ton of steps for you guys, just because I don't want this to take too damn long. When I did the math for this, I wound up getting 768 PA to the fourth power times 1 minus nu squared all over 10575 EH cubed. So that's our average deflection. And hopefully this definition for average deflection makes sense, because essentially what we're doing is we're integrating position over both the X and Y direction and then dividing by the total area of the membrane. So very similar to how we average a signal. We integrate over the entirety of one period and then divide by the length. We're integrating over the entire surface area and then dividing by the surface area. Okay. For a circular membrane, right, all of this stuff up here is going to be essentially the same, because this result is just net nominal capacitance times 1 plus average deflection over d naught, right? So if I change these limits of integration from negative a to a and negative a to a to 0 to 2 pi and 0 to a, it's still just going to wind up giving me area, right? So let me just write down here, square, and then we get an average membrane deflection of PA to the fourth power times 1 minus nu squared all over 16 EH cubed for a circular membrane. All right, I think that's enough out of me for today, and that's the last, we'll talk specifically about pressure sensors.